All right, this is the 3134 morning quiz review. Let's look at number one here. If f of x is equal to x squared minus 6x over x plus 2, does Rolle's theorem apply to the function on the interval from 0 to 6? If yes, find the value of c defined by Rolle's theorem. So just to review Rolle's theorem says that if a function is continuous on a closed interval and differentiable on the open interval, and the endpoints have the same y value, then we can guarantee that there is a point such that the slope of the tangent line is equal to 0. So if we can guarantee that we have a smooth and differentiable curve between the endpoints of a and b, then as long as the two endpoints have the same y value, then we can guarantee that somewhere between the endpoints there must be another point where the slope of the tangent line is going to be equal to 0. All right, so the steps that we need to take is we need to first confirm that the function is continuous and differentiable on the interval from 0 to 6. If we look at this function here, the only place where there could be any breaks in the graph is where the denominator is equal to 0. So the vertical asymptote exists where x plus 2 is equal to 0, and x plus 2 is equal to 0 when x equals negative 2. So there's a break at x equals negative 2. However, as long as the interval does not include this vertical asymptote, then the function is in the free and the clear to confirm that function is continuous. So if we look, we're looking at the interval from 0 to 6, and the vertical asymptote is outside the interval from 0 to 6. So we're able to say that the function is continuous on this closed interval. Differentiability comes from the derivative. So is the function going to be a smooth curve all the way throughout? So if we find the derivative going through quotient rule here, so f prime times g minus fg prime all over g squared. And if we work all this through by expanding and distributing and combining like terms, we're going to arrive at the derivative of x plus 6 times x minus 2 all over x plus 2 quantity squared. And the only break in the graph is where the denominator is equal to 0, which is also where the vertical asymptote is. So negative 2 is not going to impact our interval. So it's not going to affect our interval. So our function will be continuous and differentiable on the interval from 0 to 6. So we've confirmed that. Now the third condition for Rolle's theorem is that our endpoints have to have the same y value. Okay, so what we need to do is we're going to have to plug 0 and 6 back into the original function to confirm that both x values produce the same y value. Okay, if they don't produce the same y value, then we can say that Rolle's theorem does not apply, and we can stop the problem there. So if we plug the first endpoint, 0, into the original function, we get 0 minus 0 over 0 plus 2, which is 0 over 2, which is 0. So if we plug 6 into the original function, we get 36 minus 36, which is 0, all over 8, which is still 0. So that confirms that the endpoints have the same y value. So all three conditions have been met: continuous, differentiable on the interval, and endpoints being the same y value. So if Rolle's theorem applies, then we can go to finding the c value. So the way we find the c value is we set f prime equal to the slope of the secant line, and the secant line just happens to be 0 because the endpoints have the same y value. So we take the derivative, we set it equal to 0. So if we set the derivative equal to 0, we only have to we're trying to find out where is the slope equal to 0. So if we're trying to find out where the slope is equal to 0, we only have to worry about the numerator. The denominator is going to be negligible. So if we set the numerator of the derivative equal to 0, we get x plus 6 times x minus 2 equals 0. So x equals negative 6 and x equals 2. So these are points on the graph where the slope is 0. However, we have to go back to looking at our interval. We only care about c values that sit on the open interval from a to b. So anything that is outside or on the endpoint have to be eliminated. We only Rolle's theorem is only guaranteeing points that fall between the endpoints a and b. So if we look to falls between the interval from 0 to 6, so we keep that one. But negative 6 is outside the interval, so we have to eliminate negative 6. So the only c value is at 2. Okay. Number 2, determine whether a mean value theorem can be applied to the function. So mean value theorem, just to review, is not as many conditions as Rolle's theorem. So we still need the function to be continuous and differentiable, but we no longer have to test the endpoints to see whether they are the same y value. We do need to use the endpoints and find the slope of the secant line. And what we're trying to guarantee is that somewhere along the graph, the slope of the tangent line is going to match the slope of the secant line. We're trying to find out where that point is. So after we determine that the function is continuous and differentiable, we set the derivative equal to the slope of the secant line, and then we solve for c. So then part B, number 2 here. Let's look to see if there's any breaks in the graph. The only break in the graph that we have is when the denominator is 0. And the denominator 0 is when x is equal to 0, which is where the vertical asymptote is. So vertical asymptote is at 0. However, this falls outside of our interval, so we can continue with our condition. Our condition passes. Function is continuous. All right, so now let's look at the derivative to see is there any point where the slope is undefined, and then we check that point with the interval. So to find the derivative, I'm going to go through quotient rule. So f prime g minus fg prime all over g squared. So f prime times g minus fg prime all over g squared. We clean this up, we get negative 1 over x squared. The only place where the slope is undefined is at x equals 0, which also happens to be the point where there's a vertical asymptote. And both these places have x equals 0, and x equals 0 falls outside the interval. So it does not fall between, it does not affect our function being continuous and not continuous or differentiable on the open and closed interval. So we have confirmed that the function is continuous and differentiable. So now we just have to find the slope of the secant line and set it equal to the derivative function. So the slope of the secant line, we can do that by finding endpoints. So we basically just have to find the slope between the endpoints. So we take the endpoints 1/2 and 2, plug them back into the original function. So 1/2 plus 1 all over 1/2 is going to be equal to 3. Plug in 2 into the original function. So 2 plus 1 over 3 is 3 over 2. So then we just do slope, change in y over change in x, which I'm going to call this average slope, or slope of the secant line. So this gives me 3/2 over negative 3/2, which is negative 1. So we set negative 1 equal to our derivative function, which is negative 1 over x squared. And we can just simply solve for x, cross product. X squared equals 1, so x equal to plus or minus 1. So c is equal to plus or minus 1. And then whatever c value that we get, we always have to check with the interval. C value has to sit in the open interval between a and b. So any endpoints or any points outside the interval have to be, we have to take those out, and those are extraneous. So let's see here. If we test 1 is inside the interval, so that c value we can keep, but negative 1 is outside the interval from 1/2 to 2, so we eliminate negative 1. We only have one c value, and that c value is 1. All right, number 3, use the second derivative test to classify the critical points as relative max or relative min. So remember, the second derivative test is using the second derivative function to determine whether a critical point is a relative max or relative min. So the steps that we take is we need to first find critical points from f prime. So from the first derivative, we can find the first derivative going through power rule. So bring down the 4, 4x cubed times 1/4, which gives us just x cubed. 2x cubed becomes negative 6x squared, and then 6 goes to 0. So we have our derivative function. We can factor and find critical points, which is at 0 and 6. So now we can plug 0 and 6 back into the second derivative function, and from there determine whether these critical points are relative max or relative min without having to go through a sign line. Okay, so if we plug first we can plug 0 into the second derivative, but let me go through and find the second derivative. So second derivative, we start off with f with y prime, go through derivative, go through power rule again. So x cubed becomes 3x squared, 6x squared becomes 12x. So we get 3x squared minus 12x. Plug 0 into the second derivative, we get 0 minus 0. So that tells us that at 0, there's an inconclusive test if the second derivative does not produce either positive or negative values, then it tells us that the second derivative test is not sufficient to provide information about whether that point is a relative max or relative min. Okay, so inconclusive test. Let's go to 6. So we're going to plug 6 into the second derivative function. So 6 gets plugged in to x, and we get 3 times 6 squared minus 12 times 6, and that gives us positive 36. Positive 36 is greater than 0. So if we have a positive, that means this is part of a concave up graph. So imagine a point that has a slope of 0, so the tangent line being 0, and also being part of concave up graph. If that's the case, then that point must be a relative minimum. So relative minimum is at x equals 6. All right, number 4, sketch a labeled graph with the following characteristic. F of negative 1 equals 4, f of 2 equals negative 1. And we have these characteristics telling us information about the slope and concavity. So from the slope information here, I'm going to go ahead and create a sign line. So I have a sign line with my critical points being negative 1 and 2. So negative 1 and 2. Positive slope to the right of 0. Positive slope to the left of negative 1. So I will indicate that with the arrow pointing up. And positive slope, f prime greater than 0, where x is greater than 2. So to the right of 2, we also have slope being positive. We have negative slope, f prime is less than 0, between negative 1 and 2. So between negative 1 and 2, we're going to let there be negative slope here. So having a sign line and these arrows kind of helps us produce a visual as to what the graph could look like. All right, we know a point of inflection is at 1, 2, so we can create another sign line for the second derivative, and we'll let x equals 1 be the potential point of inflection, or actually it is a point of inflection. We have second derivative is less than 0, so concave down to the left of 1, so concave down to the left of 1, and then concave up, so second derivative is positive, to the right of 1, so to the right of 1 we have concave up. So we want a graph with these slope behaviors as well as these concave up, concave down behaviors. So let's go ahead and plot all the order pairs first. So negative 1, 4, so negative 1, 4 goes here. 2, negative 1 goes here. And then we have a POI being at 1, 2. Right? So now we're going to mold the graph to produce these characteristics. So we want a graph that is increasing to the left of negative 1, hits a maximum at negative 1, and decreases to a relative min of 2, and then increases again, while keeping these shapes intact. To the left of 1, we want the graph to resemble concave down, and then point of inflection at 1, and then to the right of 1, we want the graph to resemble concave up. So then putting this all together, we have a graph that's concave down, increasing to negative 1, maintaining concave down, decreases to 1, changes point of inflection, and then from 1 on, it resembles concave up, but the graph is going to be decreasing until 2, and then at 2, at x equals 2, it'll increase to the right of 2. All right, let's look at number 5 on the back here. Find the absolute max and absolute min. So this is an extreme value theorem problem where we have a closed interval and we're trying to determine where the absolute max and absolute min is on the graph. So the conditions for extreme value theorem is that the function has to be continuous on the closed interval. It does not have to be differentiable. It does not have to be a smooth curve. Okay, so if we look at this, there is not going to be any breaks in the graph. If we look at the denominator, there's no x value in the denominator that will cause the denominator to be undefined. So it looks like the function will be continuous everywhere. There's no holes, there's no vertical asymptotes. So we know that extreme value theorem will hold, and we will be able to gain absolute max and absolute min y value on this closed interval. So next step, for extreme value theorem, we need to identify critical points. So define critical points, because critical points can act as a potential candidate for absolute max or absolute min. So we find the derivative function. We go through quotient rule, f prime g minus fg prime all over g squared. We can distribute, combine like terms, simplify. We get 16x over x squared plus 4 quantity squared. Okay. If we look for critical points here, the denominator will not produce any critical points. There's not going to be any x value that will that we can solve for the denominator. So if we set the numerator equal to 0, we get 16x equals 0, so x equals 0. So we only have the numerator that will give us critical points. So before we test critical points here, though, we need to make sure that this critical point falls between the endpoints, and it does. 0 falls between -4 and 4. So that gives us 3 candidates to determine absolute max and absolute min. We're going to test 0, -4, and 4. So we're going to plug each of these critical points back to the original function, and then after we plug them in, we're going to compare the y values. Whatever has the highest y value will be the absolute maximum. Whatever the lowest y value is will be the absolute minimum. So if we plug in the first endpoint here, -4, into the original function, we're going to get 12 over 20, which is 3/5. Plug 4 into the original function, we're going to get 4 squared minus 4 over 4 squared plus 4, which is 12 over 20, which is also 3/5. Okay, finally, we plug 0 into the original function, so 0 minus 4 over 0 plus 4. -4 over +4 is -1. Now we can compare these 3 y values. Looks like the largest y value is going to be a shared between 3/5, and the lowest y value must be -1. So we can say absolute max is the y value 3/5, which happens to occur at the endpoints, and then the absolute minimum is -1. That's the lowest y value, and it occurs at x equals 0.